Okay, so that's the texturing done. That's the material assignment done. So now I'm just going to move that over a little bit. And we're going to start work on reversing. So we're going to use this one, obviously. And it's actually quite simple. So first of all, it's going to be rev, or back, I don't know, whatever you want to call it. And I want another Python controller. And change the execution to module. And also hook that up to the transmotion actuator. I'm going to create another method in here called decelerate. I may not be spelling that correctly, but I do believe its derivation is from the Latin celer, or celeritas, for speed, swiftness. So there you go, that's my little nerdy comment. And it's just going to be very like the acceleration. But the one thing, of course, that we need to make sure we do here is because we now have the possibility of decelerating it. If we notice in the update method, all it's doing is slowing it down. So what happens if we're reversing and it keeps updating? Well, the velocity is not greater than 0, it's less than 0. So what's going to happen is it's just going to keep reversing at a constant speed, even when we take our finger off the down button. So we need to add in another statement here, which is going to allow for that calculation as well. So if it's less than 0, and seeing as the deceleration is actually going to be by minus 0.01, because, you reverse half as much, even less, as your normal speed. And it's not going to be max velocity. First of all, max velocity is positive. Max velocity is positive. So whatever we do to it needs to have a negative sign in it. And secondly, max velocity is 0.5 at the moment. And you don't want to be reversing at the same speed as you're going forwards. That just doesn't happen. So I would probably advise dividing it by -2. So, and if so, then subtract some more. There we go. And it has to be if velocity is greater than, because it's a negative value. So that's that pretty much done. I've said that so many times now. Just cut that out. If velocity 0 is less than 0, then it needs to add, I'd say half that again. So 0.005. So that should be pretty much it. And that's going to, of course, be bound to the down arrow, and the module is going to be game.decelerate. That looks about it. Oh, and this is every time. Sorry, activate the true level triggering. Much better. Okay. I've actually thought of playing around with some of these settings, because at the moment I think it's a bit too, I don't know, the top speed isn't as good as it is as I'd like it to be. I think it's a bit too slow, actually. If you look at that, that's a bit slow really. So I think I'm going to up the max velocity. So I'll try 0.8. Don't forget to save it. That's much better. Okay. And also, I think the actual resultant force is a bit too, because then it just stops immediately. I mean, what car does that? So I think it needs to be 0.5 like reversing as well. Yeah, that's much better. And that will certainly help when we actually come to do the turning. So that's those modifications made, and we've now got reversing working. Okay, so to move on to the turning. So first of all, add the sensors for moving right and left. Keyboard. And also we're going to want, first of all, we need an and also a Python script, because we only want the car to rotate when we're holding down the keys. And in fact, it's not going to be an and this time, it's going to be an or, because if it's an and, then both of these have to be true. So in other words, both of the right and left keys would have to be held down for the controller to actually be activated. So we're going to choose an or instead. That means only one of them needs to be running, needs to be true, in order for the or to be activated and go on to the actuator. So we're going to create that rotational motion, rot motion, and this is going to be hooked up to the or and the both of these as well. It's going to be right and this could be left. Change both of those two modules, of course. There you go. They're a bit fiddly to connect. Alright, now the actual scripting for this is going to be a little bit more complicated, because of course before we were just moving, we were just accelerating and decelerating, and that was really affecting the acceleration, which was then being applied to the velocity, and Blender was then applying that within the game to the actual location. This is slightly different, because as you should be aware, the actual turning speed is dependent upon the velocity. Because of course when a car is stationary, the maximum turning speed is 0. You can't turn. It's because the car isn't moving at all. And when a car, when it goes too fast, when it goes very, very fast, will actually limit its turning speed, because it's actually throwing itself with so much energy forward that it struggles to get around the actual air resistance and the friction on the ground that's being generated by the speed. And there is also an optimum point where it reaches a certain speed where the actual turning speed is going to be at its fastest. So we need some kind of way of calculating this, and this is where the maths comes in, and more specifically, this is where quadratics come in. Now I might mention them in the previous tutorial, because I normally use quadratics for everything, because they are so useful. And for those of you who have taken O-levels, I know that's certainly the European equivalent. I'm not sure about American equivalents or anything like that, but O-levels, A-levels in maths, then you'll probably have started learning them and thought, what is the point in this? It's a curve. Well, I didn't, but that's just me. I know a lot of my friends did, and the real point in quadratics is exactly this, and you're about to see why. This is a function graph plotter from RLS Maths, or what's his name's, and you'll find this on the website www.sharp-maths.com, and underneath here there should be a function graph plotter right here under online resources. This is actually brilliant, and it's helped me out a lot over the years. And if we have a look, I'm going to just draw a normal line. There's a sort of missing y equals. See, just that's what it means. Y equals x. Just if I put x in, these values here are the minimum and maximums for the axes, and this is the actual graph, the equation of the graphs to draw. So y equals x. That's the most simple. So what we're going to start doing is now thinking of graphs as actual functions, as if they were functions within a script, and the two axes being inputs and outputs respectively. So for instance, if I think of the x-axis as an input, if I input the value 1, we follow this up and where it meets the line and then go across. If we look at the y-axis, we can now imagine 1 as being an output, or vice versa. So 2 would produce 2, 3 would produce 3, 4 would produce 4. And this is just with the line y equals x. Now if I was to translate that line, y equals x plus 2, we can now see that the inputs and outputs, their correspondence has shifted. So if I input 1, for instance, it comes out 3. If I input 2, it's going to come out 4, and so on, because the whole thing has been shifted by 2. So you can see that graphs can now be thought of really as functions, with taking inputs and giving out outputs. Now, if we're thinking of turning, remember, what we're trying to envisage really is a curve, because it starts off at 0 in terms of turning speed, and then it increases and increases and increases up to the optimum velocity, and then as the car accelerates even faster, it's going to decrease and decrease and decrease. So what we're really forming is a curve. Now I'd like you to try and picture that in your head, if you can, because I'm willing to guess it's going to look something like that. So there is our basic quadratic, y equals x squared. Nothing particularly exciting about it. Not yet. Now, this is really where the maths comes in, because we need to find the perfect quadratic for our set of values. Now, we know the maximum speed at the moment is 0.8. So if we times up by 10, just to get a more friendly number, then we know that the value, if we input a value of 8 in the velocity, we want to get, if we input a value between minus 0.4, because remember, for reversing it's half that, minus 0.4 and 0.8, and minus 4 and 8, we want to be able to get a set of values which are going to give us our proper turning speeds. So how are we going to do this? Well, if we look here, these are the two most important pieces of information about a quadratic. First of all, where it cuts the x-axis. If we look at this graph here, we can see that it cuts the x-axis at one point at the origin, 0, 0. Okay, so the graph can be factorized into x times x, because of course it's x squared. So x times x equals 0. Okay. Now, if you don't know what I mean by factorize, then you might want to just skip the next couple of minutes of this and copy down what I put. For those of you who have taken higher education, such as A-levels, obviously you will know everything about what I'm talking about, especially if you're taking some sort of equivalent to C1. Anyway, x times x equals 0. That's just the normal x squared. But what if we want to be able to predict? What if we want to actually find out what our equation is from where it cuts the x-axis? Because if we think about it, where it cuts the x-axis, we're going to input a value, and the output is going to be 0. Because if I change this, for instance, to minus 2, that shifted the whole graph down, and there are two places, 1.2 and minus 1.2, where if we put those values in, they will come back with a value of 0. Alright? So, what if we want to be able to find, so we know there are 2 points where we're going to have a turning speed of 0. The first one is when the car is stationary. That's when the velocity is 0. So if we think of the input as the velocity and the output as the turning speed, then things will start to make sense. So if we input a velocity of 0, we want to get a turning speed back of 0. And in order for it to decrease past the optimum velocity, we need there to be some really, really high speed where the turning speed is also 0. Okay? Now, because we have a limiter of 0.8, we can just set it to something like 0.9 and not worry about it, because we're never going to physically reach 0.9. In fact, it's almost physically impossible. So instead, we know that there are 2 points where it's going to equal 0. 0 and 9, because remember we're timesing everything by 10 to make it slightly easier. So if we break this down, those of you who have factorized quadratics and done all of these horrible things will know that in order to get an x value of 0, one of the parts of the factorization must be just x on its own. So I'll just put that in brackets, x. And there should be another set of values, another set of brackets. And inside of these, we want the solution to be equal to 9. So the answer for that is going to be x minus 9. Because if we break these down, x equals 0, well, we know what that is. X minus, so x is going to be equal to 0. X minus 9 equals 0 can be rearranged as x equals 9. And these are the 2 points, 0 here and 9 here, that we want it to be equal to 0. Again, if I've lost you, I apologize. But this is where the maths comes into play, and this is also why I didn't include this in the previous couple of tutorials. So do feel free to just copy and paste. Right, so we now have our where it cuts the x-axis. So we now have all the information we need really to create the quadratic. So if we times these out, x squared minus 9x, easy peasy, equals 0. So that's our finished quadratic equation. That wasn't too hard, really, was it? Secondly, the vertex. Now, if I was doing this, if I was doing this for a proper game, I would be worried about the vertex, and would probably do some sort of calculations to get that perfect minimum maximum point. But this isn't really a proper game. You know, this is hard. This isn't industry. If you would like to try and work out some way of, if you would like to try and do the maths and put in your own maximum speed in terms of turning, then this is how you do it. You use the vertex to manipulate. You use the vertex, make the vertex equal to 0, 9, I think. Yeah, if you make the vertex equal to 0, 9, then you can work backwards from there to manipulate this original equation into giving you the perfect one. But you don't. For this, I'm not going to bother because I don't really need it. So this is our finished quadratic equation. However, let's put that in for now. Minus 9x. It's very, very big. So we're going to have to change that to, I'll make that 10. I'll leave that as minus 5. I'll make that 10 as well. So you can see it's clearly cutting the graph here at, if that's 2, 4, 6, 8, 9, and 0. And that's exactly what we want. However, yes, there's a however. If we look at the graph, if we put in a speed, say, of 4, the turning speed is going to be minus something. That's not good. At least for one of them. Because if you think about left and right, one of them's going to be negative, one of them's going to be positive. So I like to work with positive to begin with. Makes things a bit simpler. So, as opposed to this original equation, we need to make it negative. So we need to times minus by everything. Or, if we just do that now, manipulate it mathematically, we now have a different equation, minus x squared plus 9x. So that will give us a positive instead. So this is our finished equation right here, minus x squared plus 9x. Let's go ahead and put that into Python. This is probably the point to resume if you are completely lost over all that math stuff. So here, I'm just going to create the function for turning right. We need to do the same also in our main class. Now, with this, we are only actually going to be affecting one axis of rotation, and we may well alter the blend file at some other point and have something which alters the other axes. So we can't just set their values to 0 all the time. We want to be able to retain their current values. So we need to store a value for that. And you could well be wondering why this is 0, because I mean surely that would be exactly the same as the first one, which is the trans motion, and we're not trying to influence that one at all. Well, if you are, then I did say in the first tutorial that this collection here is actually the actuators which are connected to the controller. So in this case, it's actually the first item, which would be rotational motion, because that's the one that's actually connected. So don't worry about that. So, and as opposed to delock, we want derot. Okay, now for the actual quadratic. So something like new rot equals. First off, I might just assign something to x, just to make it a bit easier for you to see what's going on. X is going to be the current velocity. And with this turning, just in case there's something weird going on and the turning happens first, I'm going to set the velocity to 0 instead of none. Because if we try and do numerical operations on a none, you will get an error. So x equals self.velocity. So new rot is going to be the result of that quadratic equation. So first of all, we need x. Now this is how you do squared in Python, or use an index, is by using two multiplication signs. So that's x raised to the power of 2. And we want to times that result by -1 to make it negative. Then we want to add 9 times x. And that's that. However, remember, to make it easier for ourselves, I've decided to times the velocity by 10, just to make the equation work properly. So that's the new rotation calculated there. Now this is turning right, actually. So yeah, well yeah, I'll just leave that. So this is the new rotation. So now what we want to do is actually apply it to our rotation. So I'm just going to copy that again and change it to drot equals mathutils.vector, and let's have a look. Change it to the local space, and I mean I might even just change that to rotation, and we can see that the actual axis we want to rotate it on is this blue one, and that is indeed the Z. Alright. So in this case it's going to be rot, if we get back the original values, rot 0, rot 1, and finally our new rot Now, if we're thinking about it, new right at the moment is going to be some sort of value like 9. That's just over 9. It's going to be somewhere near the maximum. So, if we're applying this, first of all, we're going to want to do something with it. We're going to want to divide it by 100 to get 0.09. Yeah. To get 0.09, but if we have a look, 0.09 is a lot faster than our normal acceleration. A lot faster. So that's not an appropriate value. So we actually need to divide it by 1000, which is going to give us 0.009, which is slightly faster than our resultant force. So that is an acceptable value. So there's our vector that's going to be applied. Now let's just find out whether it's in the right direction, or whether we're going to have to make it negative. Because, of course, if we're turning both right and left, one of them is going to be negative. And if we hook these up, right arrow, car dot turn right. And that's set to there. Oh, hang on. It's not car, it's game. We should probably fill something in for that as well. And also turn on. Okay, that's way too fast. Something's not being subtracted. Because the quadratic's fine, so something's going wrong with the maths. Let's have a look. Oh, look, there we go. It's supposed to be -1. And save it. There we go. It's very nice. So as we speed up, there we go. Proper turning speed. So as you speed up, the turning speed slows down. Probably see it better like that. It goes to a halt. There we go. There, that's pretty cool. So that's that sorted. So all we need to do is duplicate the turn right and make it turn left instead. And I think actually, yeah, right is in the opposite direction. So this needs to be divided by -1000. That's all you have to do. Turn left is going to be exactly the same. And I'm keeping them separate just for the sake of organisation. And just, you know, it's neater. And don't forget to name that one. So that now, right, divided by 1000. There we go. So that now everything acts as should do. Very nice indeed. I could do this all day. Alright. Well, I might actually tidy this up a bit before I release it as a finished blend file. But apart from that, everything will be exactly the same. Okay. And I might fix those lights at the front. I think they're a bit too bright. But the motion's all working very nicely indeed. So in the next part of the tutorial, I'm going to tidy everything up, and we're also going to do the motion on the wheels.